Hello and welcome to part 3 of the Demystifying Fiber Optics series by the FiberWizards. In this section, we'll take a high-level view of how fiber optic systems work. Ready? Let's go! As we have established in earlier sections, fiber optic systems work with light signals. An example of information transmission using light signals will be flashing a message in Morse code with a flashlight, with someone on the other end receiving and decoding the light. In fiber optic links, transmitters are used for converting electrical signals into light signals to send over the fibers. At the opposite end of the links, receivers use photodiodes to receive and reconvert the light into electrical signals. Since optical links generally require a bidirectional flow of information, most optical links use transmitters and receivers combined into single devices called transceivers. As you probably guessed, the word transceiver comes from the combination of the words transmitter and receiver. To better understand some of the terminology related to light signals, we might also need to review the electromagnetic spectrum, which will help us define the range of wavelengths in which fiber systems operate in. Specific points in the spectrum are defined according to their wavelengths expressed in nanometers, which in the visible spectrum represent colors. However, in fiber terms, these are used for identifying transmission windows in the optical systems. Colors visible to the human eye are in the range between 400 and 700 nanometers of the electromagnetic spectrum. These range from violet at one end to red at the opposite end. While colors with wavelengths shorter than violet are referred to as ultraviolet, colors with wavelengths longer than red are referred to as infrared. Fiber optic systems typically use transceivers that operate in the infrared range between 800 and 1600 nanometers, which is beyond the range of human vision. Due to this, caution is required when working with these systems to avoid possible eye injury or even blindness. Some important points are that the longer the wavelength, the faster the signal and the more resistant it is to attenuation, enabling longer distance range. This means that transmitters operating at longer wavelengths are best for long-haul links. Well, so what is attenuation? Attenuation is just a fancy word for the loss of optical power as the light signal travels through the fiber. Optical attenuation is caused by intrinsic and extrinsic factors. While intrinsic factors are caused by the materials in the fiber, extrinsic factors are those caused by mechanical stress on the fiber. Among intrinsic factors, the one that affects fibers the most is known as Rayleigh scattering. Rayleigh scattering basically occurs when light collides with elements of the glass along its path, making the light reflect and disperse in all directions. Perhaps with this example, you can see how the light reflects and radiates in all directions as it travels through this acrylic rod, just like the lightsabers in Star Wars. Another natural phenomenon that causes attenuation in the fiber is called absorption. The absorption effect is wavelength specific, so it impacts each wavelength differently. Perhaps one way to visualize this phenomenon will be to observe how colors of distant objects on the water seem blurred or lost, but as we get closer to them, the absorption attenuation decreases and the colors become clearer and brighter. In addition to the intrinsic factors, there are also extrinsic factors, including junctions such as connections and splices that might cause for some of the light to escape, as we see here in this example. Attenuation is also caused by excessive bending or mechanical stress, which can cause the light signals to hit the fiber cladding at sharp angles and escape. As a general guideline regarding the minimum bend radius, or the maximum curvature tolerated by the fiber, is not to bend the fiber cable in a manner that causes a radial curvature of less than 20 times the size of its outer diameter during installation, as well as not causing a bend that creates a radial curvature of less than 10 times the size of the fiber cable diameter when stored. On the left picture here, we can see large rings in what we typically call a figure 8, which are made to prevent kinks or damage to the cable during installation, as well as smaller rings on the right for long-term storing of the fibers after splicing. Well, we've reached the end of this section. Please take a few moments to complete the quiz, and when ready, please continue with the next section. Stay safe and see you soon.